All right, so now we move on to lesson 4 of polynomials, and it's the distributive property. So the distributive property is something we've seen all the way through grade school, and if we take a look at exactly what this distributive property is, it says, what if I have some form of coefficient term, and that could be a monomial, a binomial, it could be a bunch of different things. And by distributing that term into the brackets, I can drop the brackets. So for example here, if I have an A coefficient, and I distribute that in for B and C, well then I can drop the brackets because I've multiplied A to B and A to C. What was the operation between them? It was addition. And vice versa, you could have a coefficient on the end and do the same distribution. It works the exact same way. I would have a B times an A and then a C times an A. Does order matter in this case for multiplication? Definitely not. We could have the A before the C, such as here, A before the C or C before the A. Either way, when two numbers are multiplied, their order doesn't matter. Now, if I look at the second case with subtraction in the middle, everything is the same. Now I'm just subtracting the two terms. So I would distribute my A, that gives me AB minus an AC. And vice versa, we could go from A being on the backhand side here, and then we distribute A to both. And like we said before, the order doesn't matter. Here's the piece that we need to add to this example. If I do A times B, well, that's our first component here. But I also need to do A times a negative C. Therefore, we subtract a CA. So that's our only piece missing there. All right, let's work through a couple examples based on this distribution property. So I'm going to look at my first example here. If I distribute, or I take the leading term here, or the coefficient term, and I distribute it to each of the three involved in this trinomial or a polynomial with three terms in the brackets like this, then I know it's going to be equal to, if I distribute this one, and this one, and multiply them together. So this is equal to, well, 3 times 2 is 6, and x squared times an x1 is equal to x3. And we know that by product rule because we add their exponents. Now I move on to the next term. Negative 7 times 3 is negative 21. And I put together my x squared and my y. I can't combine them, but I can multiply them together because they're different variables. Now finally, I have a 2 times the 3x squared. This is plus 6x squared. All right, now we would look and we would say, is there anything we can combine here? No, because we have different degrees on each of these and they're all unique terms, meaning I have an x cubed, an x squared, and an x squared times y. Those are all completely unique, meaning I'm not going to add these coefficients together. All right, now if I look at my second example here, well, I have 9 minus 2 times 3x plus 5. If you were to start the problem by doing 9 minus 2 is 7, and then write out 3x plus 5, we would be misguided. Why? Because we cannot just subtract. Subtraction never comes before multiplication in the bedmass. So if I have 9 minus 2 here, 9 minus 2, I'm not going to do this right away. I have to distribute the negative 2 in by multiplication, and then once I've done that, then I can combine by addition or subtraction. And yet again, we know this because of bedmass. So I'm going to leave my 9 originally and go subtract. Negative 2 times 3x is negative 6x, because 2 times 3 will give us that 6, and we attach the x. And then finally, I have negative 2 times a positive 5. This is negative 10. So which ones can I combine? Well, I see two whole numbers with no variables on them, or what we call in the polynomials unit the constants. And this is equal to 9 minus 10, which is negative 1 minus 6x. Now I could expand upon this further and say, what if I wanted this in terms of descending order of the polynomial? Well, I would have to exchange the order, negative 6x minus 1, because we know this first term of the polynomial has a degree 1, and this one has a degree 0, which we could represent by saying x to the power of 0 if we really wanted, because we know anything to the power of 0 is just 1. So this would just be 1 times that negative 1, leaving us there. So this is our solution. All right. Now, let's take the challenge question. Remember from our previous lessons that if we see a negative out front here, this is really important to address right away. The negative out front to be really clear, means I have a -1 coefficient, and I'm going to distribute that to each term within this bracket. Or if we see 3 terms like this, it's a trinomial. So I'm going to distribute my -1 into the brackets, essentially multiplying each term by a -1, flipping their signs to the opposite. Now, if I start at the beginning here, I have 3 times a 2x squared minus 7. I have to go one by one and multiply the 3 in through the distribution property. 3 times 2 is 6, and then it's x squared. -7 times 3 is -21. Then I move on to my next set of brackets. I have an x times a 2x, x times a 5. This will give me plus 2x squared, plus 5 times x is 5x. And now I can distribute the -1 through. So when I distribute my -1 through, it becomes -8x squared. The -1 times the 5x becomes a -5x. And finally, -1 times the -7 is +7. Now, we look at this huge string of numbers and we go, okay, like, how do we handle this? There must be a certain way to handle this. Well, what I would recommend is either use different colors or different pen organizational techniques. So I'm going to color all my x squareds with one color. So I have one here, and my -x squared, or -8x squared. Now I'm going to switch colors and I'm going to go, what if I color all my x terms, including their coefficient, with the other color? And then finally, I'm going to take my blue marker, or my third color, and color in the ones without variables, or what we call our constant terms. Now this becomes really easily visible to see which ones go together. We have 3x squared terms, we have 2x terms, and we have 2 constant terms. We're going to add all those coefficients together. Now, what if you don't have different colors? Here's a way you can organize this. If you just have a pencil, here's what you can do. I'm going to underline all my x squared terms with a single line. I'm then going to go to my x terms and underline them twice. And finally, I'm going to go to my constant terms and do a little squiggle underneath them. That becomes very easily visible of, oh, I have my x squared terms with a single line. I have my x terms with a double line. And finally, my constants with a squiggle. Whatever way you do this with different colors or squiggles or lines, you need to organize this, because when you get to a test, adding these coefficients properly is very important. Now, all my ones with the yellow or the single line underneath them, I have 6x squared plus 2x squared minus 8x squared. That's positive 8x squared minus 8x squared. That's actually 0x squareds. I then move on to my green, or my double underlined x terms, 5x minus 5x, that's plus 0x's. And then finally, I go to my constants, or the blue terms. -21 plus 7 is -14. Now, the nice piece about this is I know my 0 terms are going to go away, and this leaves me with just -14. So you should get an answer of -14 here. All right. So now it's the check your understanding section. Make sure you practice.